Hi guys! In this video we're going to cover solving equations with variables on both sides of the equal sign. Since we've already done one-step, two-step, and multi-step equations, now we're going to get into the fun stuff. What do I do when there's variables on both sides of the equal sign? Let's get started. So first, to just real quick kind of review the gist of what you're doing when you solve an equation, you're doing what's called isolating the variable, right? When we isolate the variable, we're trying to get it so that there's a variable on one side and there's a constant number on the other side of the equal sign, right? And when we isolate the variable, you're eliminating all the numbers that are on that one side of the equation with the variable so that there's a constant on the other side and only the variable on the left, right? So for this one, you guys know how to solve these. If we subtract the 1, we'll get 3x, and then if we divide by 3, we're going to get x, right? And on the other side, we do the same steps, and eventually we're left with the variable on one side, x, and a constant on the other, 1.5. That's how we solve equations. Now, it can be the other way around. For example, in this equation, I have 25 is 2x plus 3, so I have the x on the right side of the equation. That doesn't really matter. Our goal will become to get the constant on one side and the variable on the other, right? I can have x be on the right side of the equal sign, and that's okay, because the equal sign just is like the scale. It's the center of the scale. It just means these things are equivalent. It doesn't mean this is the answer. So for this, if I took away that 3 constant, I would get 22 is 2x, and then divided by 2, I would get that 11 is worth x. So again, I have the x on the right, and that's fine. My goal was to get a constant number equivalent to my variable, and I've done that. Okay, and I did that by moving all of the numbers to the side away from the variables. And again, it's sort of like a scale. Like here, I have a scale, I have some stuff on one side, and I have the weights that they're equivalent to the other. If I wanted to know what it's worth, I would have to move that stuff so that I could have the variable on one side, the unknown, and then what it's worth on the other, right? And I can switch that scale and have the same situation, and I'd still have to move so I'd still have to move that stuff so it would be what it's worth on one side and the variables on the other. Okay? Well, what does this have to do with equations with variables on both sides? Well, imagine that same scale, but now you can see that I have the stuff on both sides and I have the weights on both sides. Well, if I want to know what it's worth, I'd have to move all of the weights to one side and I have to move all of the other stuff to the other so that I could tell, hey, this is the unknown stuff, the variables, and this is what they're worth, right? And I can do it, I could flip it the other way around as well, where if I do the same thing, I would still have to move it so that I have the unknown thing on one side, the variables, and I have what those things are worth on the other. So that's our goal here. So we're isolating the variable and we're isolating the constant, and we're doing it to both sides. So we're saying, okay, this side is going to be for variables and this side is going to be for constants. So let me show you how it works. So here's example 1 from our notes. So it says 4x plus 7 is equivalent to x plus 10. So you can see how there's algebra terms on both sides and there's constant terms on both sides. So the way that I attack this is, remember, I'm either going to have the variables on one side and a constant on the other, or I'm going to have a constant on one side and a variable on the other. And I can make that decision whichever way I want. Both will work as long as you're doing the math accurately. But what I'm going to tell you to do is to try to always keep the coefficient positive, because that will come in handy later, and you'll see what I'm talking about in a second. So here's what I do. When I'm solving an equation like this, I look at the two algebraic terms. So I have a 4x and I have a 1x. And I ask myself, of those two terms, which has a greater coefficient? And I can see one's 4 and one is 1. So 4 is higher, right? The 4 is a higher coefficient. So what I'm going to do then is I'm going to make that side, the side that has a greater value for my x, I'm going to make that side into my variable side. And by doing that, I'll keep the coefficient positive, and you'll see what I'm talking about. So I'm going to make it variable on the left because I have the more of the x's on the left and the constants on the right. Okay, again, keeping the coefficient positive will make things easier, especially later. So in order to do that, in order to make it variable equals constant, I'm going to start to move things around. So first I'll move the 1x that's on the right side, I will move that to the left side by taking it away. I'll take 1x away from both sides, and that gives me 3x plus 7 is equivalent to positive 10 or plus 10. Now I just have a two-step equation. Just that one step alone has now transformed the equation where I have a two-step equation. So I'll move that 7 to the other side, because remember, I'm moving the constants to the right side. So I'll take away 7 from 10, that gives me 3. I'll bring my 3x down, and then I'll divide both sides by 3, and I get x is equivalent to 1. So in the end, I have my variable on the left, that's what I decided, and my constant on the right. Right, so x is 1. And just to double check it, I can plug that 1 back into the original equation. So 4 times 1 plus 7, is that equivalent to 1 plus 7? Well, 4 plus 7 is equal to 11. Yes, that is a good to go equation. My solution is correct. I know that, okay? So here is another example. In this example, it says 8 minus 5x is equivalent to 2x plus 22. This is the second example on your notes. Now for this one, again, I'll start by asking myself, am I going to do the variables on the left and the constant on the right, or am I going to do the constant on the left and the variable on the right? Some people always do the variable on the left. They just like it to say x equals at the end. And that's fine, but you're going to notice here why that can actually mess you up. So I'm going to go with my method. I'll look at my two algebraic terms, and I have negative 5x on the left, and I have a 2x on the right. And when I look at those two terms, I can see that which one has a greater coefficient? Well, 2x is a higher coefficient than negative 5, right? So to that side, my right side, is where I'm going to move my variables. I'm going to make that the side where I isolate x. So in order to do that, I'm going to have it be constants on the left, and then, like I said, variables will be on the right. So first I'll move that 5x. I always move my algebraic terms first. You can move the constants first, it doesn't really matter, but I'm going to move my algebraic term first. So I'm going to get rid of that 5x from that left side, because that's the side I want my constants on. I do that by the opposite, which is add 5x. If I add 5x to negative 5x, that's 0, that's gone. And then 2x plus 5x is 7x, right? I'll bring down the 8 and the plus 22. So now I have a two-step equation again. Again, I'm moving the constants to the left side of the equation, so I'm going to get rid of that 22. I'm going to take away 22 from both sides. That's going to give me negative 14 is equivalent to that 7x. And I have just one more step to do, divide by 7. That gives me that negative 2 is equivalent to x. So there I have it at the end. I had constants, negative 2, and then I had variables x. And I just kept working until that's what I got to, all right? And if I check that, I can check the math. And negative 5 times negative 2 is 10, and 2 times negative 2 is 4, or negative 4, sorry. And so 8 plus 10 is 18, and negative 4 plus 22 is 18. So guess what? Checks out. It's good to go. Now for this one, I am going to show you what would happen if you were just always bringing the variable to the left side. So same equation, okay, but this time I'm going to bring the variables to the left. So first I'm going to move the constant term. So I'm getting rid of that 2x. I'm going to take it away. Here's mistake number one that people make when they do this. Already I have negative 5x minus 2x, which is negative 7x, right? So there's already a mistake that some people make right there, because I'm already dealing with negatives more often than I would had I been doing the method that I just showed you, right? Because if you do it this way, sometimes you're dealing with negatives way too much. If you do it my way, you're dealing with negatives less, which means you're less likely to make a mistake. But I moved the 2x over by taking away 2x from both sides. Now I got to get rid of that 8. I got to take it away. Remember, even though that second term is minus, 8 is positive. The constant is positive 8. I got to take 8 away. I take 8 away from both sides. I get negative 7, because that minus stays with that negative 7. There's another mistake. People forget to bring that down. And I get 22 minus 8 is 14. Last step, negative 7x is equivalent to 14. I have to divide, not by 7, by negative 7. Another thing that people sometimes mess up. And I get x is equivalent to negative 2. So I still got the same solution by moving variables to the left, constant to the right. However, by not keeping the coefficients positive, you're opening yourself up to make potential mistakes, right? You get the same solution as long as everything is correct. But the math is a little bit more tricky because, like I said, you're dealing with more negatives and you're opening yourself up to make a mistake. That's why I do it this way. All right, I'll just go through these last two examples quickly. So here is example 3. First of all, don't like the decimals. They're all one place value, right? 2.9 and 2.7. So I know if I multiply both sides by 10, I can eliminate those decimals. I'm going to do that right now. So I'm just going to distribute the 10 to the left side and 10 to the right side, and that gives me 29y plus 27 is equivalent to 11y minus 99. Okay, I like it already because now it's whole numbers. So again, looking at my two algebra terms, I notice that 29y is higher than 11y. So I'm going to keep my y's on my left. I'm going to make it variables on the left, constant on the right. I'm going to do that by taking away 11y from the other side and from the front side, right? Take it away from both sides. That gives me 18y is equivalent, or plus 27 is equivalent to that negative 99 now. And then if I take away that 27, I get the 18y is equivalent to negative 126, because remember, you're adding those absolute values when they're both negative there. And then the final step is divide by 18, which hopefully you have a calculator on your hand, and that ends up to be y is negative 7. Okay? So, again, notice that there was more y's on the left side. That's why my y I left on the left side there. Also did the times 10 trick for getting rid of those decimals. Highly recommended. On the last example here, I have a bunch of fractions. Now, some of you are just going to deal with them because you're allowed to use a calculator and you don't care. Not me. I don't like fractions, so I'm going to get rid of them, right? So I'm going to look at the three denominators, 4, 2, and 8. Their lowest common multiple is 8. So if I multiply both sides by 8, all of those fractions will disappear. I just have to remember I have to distribute the 8 to each term in the equation. So when I do 3/8 of 8 and half of 8 and 3/8 or 3/4 of 8, that is, and then 3/8 of 8 and 4 times 8, if I do all of that math, I get 6x minus 4 equals 3x plus 32. It already looks better. Now again, now I'm ready to go. I'm going to look at my algebraic terms. Now this step is easier when they're not fractions, right? I can see that 6x is higher than 3x. If I had stuck with the original one, I'd have to see that 3/4 of x is higher than 3/8 of x. You can still do it, okay? So I'm going to take away, I'm going to move all the variables to the left because that's where the higher value is for my coefficient. So I'm going to take away 3x from both sides. That gives me 3x minus 4 is 32, right? And then I'm going to add that 4 to both sides to bring the constants to the right side of the equation. That gives me 3x equals 36. Final step, divide it by 3, and I get x is worth 12. So that's the gist of it. It's just one of those things you have to practice. I highly recommend doing my method of looking to see which one is a higher coefficient and moving the variables to that side. That will especially come in handy when we start getting into inequalities, and inequalities that have variables on both sides, because that's where it starts to matter, and you'll see what I'm talking about later. So I hope this helps. Give some of the practice a try. Good luck.